Hi, I'm Albert Bloom. I'm a student working with Hartmut Geyer at Carnegie Mellon. And today I'd like to talk about some of the work that we've done towards controlling a highly maneuverable robot in 3D. Our work is in two directions. The first is we augment the 2D slit and its controller to apply in 3 dimensions to stabilize and achieve steering. And the second is verifying that using these controllers derived from the simplified models, what do they give us when we apply it to a full robotic system? So we start with the planar slit, and it's been thoroughly analyzed. One of the key results that we want to build upon is the deadbeat control and the time embeddedness of that control. So deadbeat in the sense that if you use an apex to apex mapping, you can go to your desired apex within one stance phase, and time embedded in the sense that when you describe your apex, instead of measuring your ground height with respect to where you're going to put your foot down in your next stance, you measure your flight time so that you don't have to be constantly scanning the ground in front of you. That will be discussed in a little more detail later. The 3D spring mass model has been examined. It's been shown that if you put it in global coordinates, it's passively unstable. The lateral motion needs to be stabilized through feedback. If instead you use the direction of motion from the previous apex to characterize your angles, you can get passive stability. And what we do is that we take the deadbeat time-embedded control that exists in the 2D model, and we use it to stabilize the apex height simultaneously with the steering angle in 3D. So to do that, we start by defining our 3D model. Again, we're interested in an apex-to-apex mapping understanding of it. So your initial apex is characterized by a height, and then your next stance phase is going to be characterized by a landing angle alpha and a splay angle beta relative to your previous direction of motion given by the apex frame defined with respect to your previous apex. So stance is going to occur with whatever parameters of your spring leg, and after stance you're going to get a new apex characterized by an apex height yi plus 1 and a new direction of motion, generally with some deflection d theta, and that's going to be a function of alpha, beta, and your other landing parameters. So in the highest level, we're interested in our next motion is described by a height coupled with a deflection to your direction of motion. And that's going to be a function of your previous apex height, yi, and whatever parameters that govern your stance phase. Here we treat the controllable parameters as your leg placement. So that's going to be your landing angle alpha and your splay angle beta. So then your control problem, you can treat that as if you have a desired target motion characterized by some, say, steady state apex height that you want, coupled with steering deflection that you want, d theta, you're trying to find the foot placement parameters to push through your behavior function to match your desired behavior. If you can get an exact match, that's deadbeat control. And if you can't match it exactly, your distance function d kind of governs how you trade off between your two desired characteristics. So to solve this problem, basically, we start by trying to represent your behavior function, f, which is how does your next apex height and your next rotation, how is that dependent on your initial apex and whatever parameters? Here parameters are alpha and beta, so they give you a foot placement which you can map to the ground plane. So here we have apex height, here we have deflection. You can overlay them as contours, and it's a very intuitive result. Basically, there's a critical point here in front of you, where if you put your foot down, you deflect all your energy into vertical motion. You have a highest point that you can reach, and there's no translational motion. As you radiate outward from that point, the next apex gets lower and lower, and by putting your foot out of line of this straight line, you get angular motion. So having represented the behavior function, the control then lets you just interpolate. Given a desired rotation and desired apex, if you know where you came from, you just find the alpha and beta, giving you a foot placement to achieve your desired motion. Finally, what we would like to do is to understand this control as a time policy, which is instead of using your previous apex height yi, which would require you to know where you are relative to the ground in front of you, if you can measure, say, time since your previous apex, you can just run that forward as a policy from every flight phase. And you can do that simply by realizing that if you know your landing angle and you have some fixed apex height, it's pretty straightforward to back out how long you must have spent falling before contact is made with the ground. So that lets you replace this variable yi with t, where t is measured as time elapsed since apex in the last flight phase. So finally then you have a control law, which is if you know the deflection that you want and you know some desired apex height, you can run an alpha of t and a beta of t that's going to let you track deflection while stabilizing apex height. And we show this in simulation. We take like a humanoid system, we give it waypoints in green, so that's going to give it a desired d theta. We run it over unobserved terrain with step heights up to 25 centimeters. And then it just runs this alpha of t, beta of t, and the foot placements end up as these red points, and the center of mass trajectory is as follows. Slowed down, you can see a little more about how the apex height kind of stays stable. Okay, and just to verify that this is stable long-term, we give it a randomized trajectory to let it take 500 steps. Indeed, it doesn't fall, and it tracks its apex heights pretty well. There's some error, and that's caused by the fact that the ground disturbances add energy or take away energy from the system, and that gives you a perturbation to your behavior function, so there's a little bit of inaccuracy there. Okay, so we have, in theory, a controller that works for a 3D spring mass model. That's nice and all, but as has been thoroughly discussed at this conference, we know that that's not sufficient to say, oh, we can throw this onto a robot. So we would like to see that the policies generated from our template models do give us some robustness in the full system. So to explore in that direction, we implemented a more accurate model of a 2D runner and tried to embed the spring mass motivated policy and see if we can recover this deputy robustness. So we gave it a rigid body torso. So this is, well, I'm sorry, I forgot to mention this at the beginning. We are motivated by the Atrius robot being worked on at Oregon State with Jonathan Hurst and his team. So we give it a rigid body torso. It has light legs. And while the legs are light, the geared actuation at the hips give it significant hip inertias. So we still have to worry about that, meaning if you try to drive your swing leg to some placement, it's going to have a drastic effect on the torso. And then we give it a full ground contact model as well with dissipative energy and stiction slip. So in the interest of time, I'm not going to go over in very much detail about the other controls that we have to implement to stabilize things. But in general, we try to implement the spring mass motivated control as a foot placement policy. So we have a target foot placement behavior based on that underlying model, and we use PD tracking. And in the meantime, we have to stabilize the torso through augmented hip torque steering stance, as well as compensation of the trailing leg to even out the motion of the swing leg. So we embed the policy through the swing leg placement. We put it in simulation, and indeed, we observe that we can get a humanoid runner with reasonable blind tolerance to ground disturbances. So this makes us believe that if we do derive our models from the spring mass model and give it this deadbeat stability that doesn't need to observe the ground, it still will give us good behavior in the full system if we treat it properly. So in summary, we've extended the deadbeat time-based control from 2D into 3D to combine apex stability with directional tracking. And we've started to examine how can we use these template-motivated controllers in real robotic systems. And our natural next step is to try to embed the 3D model into a robotic system. And we're very interested in what can be done in terms of expressing things as functions of time instead of, say, needing to explicitly measure the ground height.
Okay, great. Thanks, Albert. Questions? Yes, sir.
So with the 3D steering, you
Yeah.
countered as the control variable for alpha basically is placed with the foot. Have you considered what you might be able to gain if you also added the spring stiffness as one of the control parameters?
Yeah, that's good.
Can you repeat in brief?
Oh, yeah. He said we were using alpha and beta as two control parameters to track what we needed, and there's other parameters that could be controlled, say spring stiffness. And right now, using just these two parameters, we have a very simple to use match of dimensionality because we have two things that we want to track and two controllable parameters. Adding one more would give us a set of solutions that's larger than our set of goals, so then we can have one additional thing to pick. So for example, that might allow like a foot, multiple points that you can stick your foot for the same behavior in terms of theta and yi, and then you can pick among these, and you might get like a choice of where you put your foot, if you could vary gain, or any other foot.
They also, you have to be putting the real leg on it, you may not be able to do it as quickly as you want, so you have to have the wiggle room, those solutions.
Yeah, that's right.
You sure that there's a range that you do have answer for, you do have possible answers to have the control? I'm wondering if the parameters is based on the HPS just or dimensionless parameters that can be extended to any other, for example, for the parameters of birds as well as humans as well as
I see. The question, I believe, is our region of stability based on Atrius's parameters. The control, actually, when you try to back out your control policy, the things that tend to matter the most are your target apex height, as well as what kind of ground contacts do you allow. So what's your friction component, and that falls out pretty naturally from the design process. And what you do see is that you can generally see how the variation of parameters changes your policies. And indeed, some pretty intuitive results are like if you reduce the amount of friction you allow with the ground, you can only achieve wider turns instead of doing instantaneously tight turns. And yeah, it's not based on Atrius itself.
Okay, we have a question.
Sorry.
In your simulation model, you have some trunk, but you spoke about the control of the SD model. I want to know, do you have any ability to control the trunk too, or?
I'm sorry, I'm having trouble hearing you. If someone closer heard you?
In your previous slide, you showed some simulation model with the trunk.
With the
I
trunk?
want to know what was the control approach for the trunk. Do you use it for?
The control approach for the trunk.
Oh, yeah, in this guy? With the control approach for the trunk. Okay. Most generally, we try to actively stabilize it in stance. So we try to feed forward, cancel out the torques applied through the ground reaction force, and we also need to cancel out the swinging of the swing leg. So we do that by augmenting a hip torque here in stance. And then in flight, again, the swing leg is going to create a moment on the trunk. So we try to cancel that with your trailing leg.
Did you have one? It's okay. Okay.
If that's okay.
Did you have a quick question?
Kind of a sort of answer that section.
Okay. One quick question. We have time for? Yes.
Time from Apex. It's stored as a two-dimensional table. I don't think it behaves very linearly, but the resolution doesn't have to be that fine. It's pretty well behaved, but I don't think it's just straight.
Okay, that's good. Thank you, Albert.
Thank you.